Hello, everyone. Welcome to today's virtual lab session. And in today's lab, we will be talking about the important process parameters and the equipments and the methodology we follow in order to calculate these values. Okay, so we'll also briefly see the principles based on which these equipments work, and we will show wherever possible some demonstrations of using these equipments. Okay, so we really hope this is helpful for you, and someday when you guys going to use these equipments, these instructions are helpful to you.
The measurements that we do in machining and manufacturing processes are for parameters that help us understand the process better, or in numerical studies, parameters that help us to validate the model that we have built, right? So what are these significant parameters? So usually, the four that you see here, the surface roughness, which is measured in micrometers, the cutting forces, the temperature, and the tool wear. These are the main or the most generally sought after parameters that we want to measure in machining or manufacturing processes. Okay, so in today we will see what are the equipments that we use, some principles based on which these measurements take place, and the general methodology that you have to follow in order to achieve good results. So one of the basic methods and the most easiest to use method is a direct contact based surface roughness testers. So in these kinds of surface roughness tester, you have a vertical stylus that moves along the surface, and we are able to calculate or know the value of the surface roughness. Okay, these are handheld devices and user friendly, and we also use the same type of surface roughness tester in our AML lab. Okay, and the other type of methodology or the method or the instruments are non-contact based instruments. Some of them use laser technologies, microscopes, and optical interferometry. Uh, these methods are non-contact based. So one of the advantages of these methods is you're not touching the surface. So the chances of damaging those surfaces are, you don't have this particular limitation that you have with the contact based method. So we will see how the contact based surface roughness tester works, and we'll talk about the principle of a contact based surface roughness tester in the upcoming slides. The basic principle of a surface roughness tester involves the vertical stylus moves along the test surface, and when moving along the test surface, it detects the crests and the valleys on the workpiece that we want to measure the surface roughness for. And this vertical displacement of the stylus is converted by a transducer into variance in the inductance of the coil. Okay, this is how and this variance of course is calibrated into giving us the surface roughness values. So some of the common characteristics is it has a diamond tip as its stylus, and the transducer modulates the displacement to changes in the inductance values, and gives us the surface roughness value for that workpiece. One of the limitations, as we spoke before, is that the probability that you would damage the work surface is high in a contact-based method, whereas in a non-contact-based method, you overcome that limitation automatically. Okay, as we saw that as the vertical stylus moves along the test surface, it generates a profile like this. Okay, so what you see in the graphs at the bottom here are nothing but the vertical displacements of the stylus along the test surface. Okay, so once we have this graph, we still need to decide how are we, what parameter are we using to address the surface roughness. So in literature, we find most prominently two values, Ra and Rz, and the Ra is nothing but the arithmetical mean of the absolute values of the profile deviations, okay, from the mean line. So if this is the mean line um, uh, that we have for the graph for the vertical displacements, then the arithmetic mean uh, is the RA value, whereas the RZ value is we choose a particular length as the reference length, sampling length, and say that we choose 100 micrometers as the sampling length. So within this sampling length, we take 5 values of the vertical displacements, and the mean of these 5 values is what we refer to as RZ. So both are notations for surface roughness, but they mean very different things. How it was measured is something of consequence here. So you cannot compare an RA value to an RZ value, which would be wrong, but both are still surface roughness measurements. Okay. So now as we have seen this, I think we'll move to the demonstration of how a surface roughness test is done. And you will see that it is very easy, and all this background is just so that you are aware of how and what a surface roughness tester actually does. Okay, so let's see the demonstrations.
Okay, so hello everyone. This is a surface roughness tester that we have in the advanced manufacturing lab, and as you see, the different parts of the tester involve the probe itself, or as I said before, a vertical stylus that moves on the surface that we need to test, and it gives or measures what are the grooves or the smoothness of the surface itself. And this is the reading device that shows us what is the value of the test, that the surface roughness value. And the vertical part that you see, this one is used to adjust the height of the probe. If you are using, say, a workpiece that is cylindrical and that is 5 inches in diameter, so we need to have the surface of the workpiece in the same plane as the probe. So we use this the vertical adjuster to move the probe up and down, and the reader itself does not require the vertical adjuster, and it's a portable device that you can charge it, you can move it anywhere and do your test. So the surface that you see here, on which the probe is now placed, this is the calibration surface that is provided by the manufacturer itself. Okay, so before we go into doing any actual experimental measurements, we need to first check if the probe is measuring the calibrated surface right, and it should give us a value of 3 micrometers. Okay, so let us do this test. So I'm going to turn the power on here on the reader, and I'm going to press on start. So it shows this graph moving, and at the same time you can see that the probe is also moving on the surface. That is how it detects the grooves on the surface or the smoothness of the surface. Okay, so as you see here, the value is now 3.172, and we can safely say that the instrument is well calibrated. Okay, so I'm sure you see that it is very simple to actually run a surface roughness test, and the workpiece that I now have here is an end milled surface, and we will just run the same test again. If you notice, I have placed many other workpieces below it just to adjust the surface in such a way that it is horizontal, and I'm able to place the surface. The probe itself is very much in contact with the surface we need to measure. Okay, so we go to the reader, we turn the power back on, and we press the start button. So as soon as we do that, we see that
the probe starts to move along the surface that we want to measure. Okay, and once we have that, the reader will give us the value. And it's always safe practice that we in actual experimental setups, we conduct the test over 2 or 3 different spots on the test surface, so that we know we get a good average.
The temperature, of course, is a very important parameter in a machining process because high temperatures lead to rapid tool wear and decreased tool life. And all the process parameters that we come up with must be towards maximizing the tool life, and temperature is thus a very important parameter that we have to consider. And even the workpiece, because of the thermal expansion that takes place at very high temperatures, we cannot maintain dimensional accuracies, and built-up edge formations are also a problem. Okay, so temperature is definitely an important one, and we need to have very um, clear strategies to identify the temperature in machining processes, and therefore we have different methods to do it. Okay. Okay, so the most common method is the use of thermocouples, and the most prominent method is use of thermocouples because the result can be frequently repeated. The repeatability is very high for the thermocouples, and the accuracy is also very good. Okay, so thermocouples is what we generally use. Even in our AML lab, we have different ranges of temperatures, thermocouples that we use depending on depending on the type of process that we are in. And we'll just show you some of um, the what the data logger that we have and that we use to make these measurements. And they're not so prominent, but still sometimes because of the dynamic nature of machining, it is sometimes easier to use thermal imaging cameras. But if you go and read the literature, you will see that um, there are questions regarding the repeatability of thermal imaging cameras. And because of the chip formations that take place, it is actually not easy to identify, though you still can get some areas that probably the thermocouple can't be reached to. But because of the repeatability errors of thermal imaging cameras, um, and in sometimes difficulties in positioning them exactly where you need, they are not so prominently used. And here, just to give you an example of how it would be, how the results would look, and how you'd analyze, I put in a from a study that we have. So this is the setup the authors have come up with, and if you see the let me on the pointer so I can show you the yeah, here we are. So if you see here this one, this is a Chrysler dynamometer, or almost exactly the same as the one that we have in the AML lab, and the ones that I will um that you saw previously. And this is the dynamometer, the infrared imaging camera that the authors have used, and right next to it, what you see is the result that they have obtained. And these images that you see are the different temperature ranges. I think 281 degrees Celsius is the maximum that they have seen, and I think the material is aluminum. Okay, so this is how the results will be, but as I said, because of the repeatability and few other factors of thermal imaging cameras, they are not as widely used as thermocouples. Okay. So once again, what is the principle of operation? It's the Seebeck effect. when we study the electrical design circuits. That's how we learn it as. And basically, when you have two dissimilar metals in a hot junction, basically it generates an electromotive force, and this millivoltage that is generated is calibrated into the changes in the temperature. Okay, so this is how this is the basic principle for how a thermocouple works. Now, the next, when we go forward, we need to see, uh, we know what's a thermocouple, but there are definitely different types of thermocouples. So how do we make our decision on which thermocouple do we use for a particular process, right? So that's what we will be seeing in the next slide. So the choice of thermocouple is definitely dependent on the temperature range that we need, right? And this chart that is given by the manufacturer Omega um, is shows us the different ranges that there are, J, K, E, and T. And as you see, we are using, if you use a K-type thermocouple, which we are going to use, uh, which we use for, at least I do machining experiments with titanium and Inconel, and I use K-type thermocouples because temperature is usually, if I go for high temperature, high speeds, the speeds are, the temperature in the range is almost close to 1000 degrees Celsius, okay? So that is in a dry condition. With coolant, it's lower. So this is how you see how and decide which temperature, which thermocouple do you want to go for. And different manufacturers will have these kinds of ratings available with them. So that's what you refer first, and you sort of go into literature and see what kind of temperature ranges are you looking for, are you expecting in your machining process, and you decide. Okay. So this is the thermometer that we use in the AML lab to measure the temperature values in our machining experiments, or in for general purpose too sometimes, right? So what you see now is the data logger. This is what gives us the reading, and it has 4 channels, which means we can attach 4 thermocouples at a time to this data logger, okay? And it will give us the temperature values. That is the data cable that we use to connect the data logger to the computer and take the data that we have measured and modify it accordingly. And what you see to the right is the K-type thermocouple, which allows us to go as high as about 800 degrees Celsius, or even higher than that. Okay, so, and that's the tip of the thermocouple that we have, which is kept at the location where we want to have the temperature measured, right? So this thermocouple is plugged into the 4 different channels that we have here to get the values that we need. So we now have the data logger all set up. We have the thermocouple connected to channel 1 of the data logger, and we see a temperature value that is about 23 degrees Celsius. Okay, so 23 degrees Celsius is, of course, the reasonable value considering we are in indoor environment, and it gives us sufficient confidence that the thermocouple and the data logger is working properly. Now, the next and the very important question is, what temperature are we measuring? And generally, the most significant or generally investigated temperature is of the tool. Okay, so in machining materials like titanium, the temperature goes up to values of sometimes close to 1000 degrees Celsius. So, and temperature is one of the main reasons for tool wear, and so that's why we want to know what temperatures is the tool exposed to. Okay, so what you see here is the turning insert, and if I want to measure the temperature of this insert, I have some ways to do it. So I know I have the thermocouple, but how do I place the thermocouple at the location that I want? It's impossible to keep the thermocouple at the very tip the insert. If I want to place it at the flank face, I would have to use something like a sticky tape that is thermally resistant, but uh, there, because of the chips that are continuously formed, there's a good chance that it will be ripped off from its position. A better alternative is to go for drilled holes on the inserts, as you see is done on this particular turning insert. Okay, so allowing the thermocouple to be inserted into this hole makes it easy for it to be held in position. Another important part is it also important to see whether it's the right hand tool or a left hand tool. So what you see now here is the tool holder on which the insert is held and is a left hand tool, and this is the motion or direction in which it will be cut. So the thermocouple will be firmly placed on the uh, position that we want, and the tool holder, since it's a left hand tool, it will be definitely held in position. Okay, so for tool wear measurements have got mostly to do with capturing a very good image of the face that you want to measure, and we use microscopes for that, of course. And once you have a very good image ready, it's all about just using tools, visual tools in the softwares to get the flank wear value. So I'm not really going to go in depth about what flank wear and crater wears are. I'm sure you have done quite a lot of study on it in your lectures and in your coursework. So basically we have two very important types of wear, flank wear and the crater wear. So the flank wear happens on the flank face, and this is due to the abrasion of the flank face with the machine surface. Okay, and the crater wear is on the rake face, as you can see in the image that is shown. And the crater wear happens because of the chip rubbing against the rake face as they are flowing out. Okay, so these are the two types of wares, and I'll just show you the electron microscope that we have in the lab, and basically how do we take an image in the using the microscope. Okay, this is the electron microscope setup that we have in the material science lab. What we see now is the lens, and as we know, for any microscope, the lens is the most critical part that allows us to zoom in and defines the capabilities of the microscope itself. And we can use the the lens dial to move in or out. At the same time, we can also use the controller that allows us to move the dial of the lens. So I have placed a insert in the lens holder, on the lens table, sorry. And as I move the dial in the controller, the lens moves in and the image becomes clearer as we zoom in, right? So the tool wear calculation is basically the microscope helps us to capture a very good image at scale of this particular screen image is at the scale of 100 micrometers. So once I know at what zoom levels I can get this good image, I just set the different ranges, like what is the maximum zoom level, um, what is the left, right, top, bottom ranges for the image that I want. And once I have all this set up, I just click on create image, and the microscope, the internal software automatically stitches the image uh, based on the ranges of position that I have provided it. Okay, so The critical part is to obtain a very good image um, at levels that we would want. Okay, we can even go for lower scales than 100 micrometers. So once we have, as I said, a good image ready, the next part is of course to calculate and see what is the value of the flank wear. So we are now looking at the flank face, of course, and you can very clearly see that we have a very good and a very deep wear in the flank face. Okay, so after that, it's just about using the right tools to measure that. So as you see, I'm using a 2-point tool here, which just allows me to define 2 points on the image that I have. And I can see that I have around 240 micrometers as my flank wear, right? So this is the maximum flank wear that I have. So once again, I want to reiterate the fact that the critical part is to get a very good image. Okay, and after that, it's just about using the tool. Before going into measuring the cutting forces, we need to know what are the forces we are looking for. And the major component of interest is the cutting force, which is the tangential force that is very important to investigators. The feed force is a reaction force due to the tool moving into the workpiece, and FP, which is nothing but the normal force, also known as the passive force. The active and the resultant force are the two resulting vectors from these three components. Now, it is also important to know before we do the measurements, what kind of result are we expecting? So it is usually in most machining operations, the cutting force is the maximum value. And in some rare instances, we have the normal force that is greater than the cutting force. We also have the feed force. Chrysler is one of the top manufacturers of dynamometers and pressure sensors, force sensors. So this is a very well thought out video that I found from their Chrysler website regarding cutting force measurements and their equipments that they provide. Okay, so here what you're looking at is dynamometers for a vertical milling machine. So the dynamometer is attached to the spindle, and the wire that you see is the cable that goes into the amplifier. Okay, and the milling machine that is shown here is definitely more than a 5-axis milling machine. Uh, and as you can see, you can go with different spindle adapters. Their dynamometer is compatible with different spindle adapters, and at the same time, it can also accommodate different types of tool adapters into the single dynamometer. It is very essential because you're not doing any one type of operation in the milling machine. You do multiple operations, so the dynamometer must be capable. So once you have the experimentation done, like how we had a data logger in for the thermometer for the measurement of temperature, we use a software called DynoWare that helps us analyze all these results and the graphs that we saw. Okay, and it is a very important aspect that we will speak about as we go forward. So now as we are done with the milling machine, I just wanted to show you how it would look like in a CNC turning machine. Okay, so the dynamometer, what is shown here is a static dynamometer because the tool is now fixed and the job, the workpiece is the one that is rotating, right? So it's the static dynamometer, a piezoelectric dynamometer, on top of which we attach the uh, tool holder with the insert, and the experiment is then conducted in the normal way as you would. Okay, and once again the reading is taken into the DynoWare software through the amplifier. What you're seeing now is an orthogonal machining setup that we have in our AML lab, and the tool holder is attached on top of a 9527B Chrysler dynamometer. It's once again a piezoelectric dynamometer, and we want to measure the forces in orthogonal machining, and we know that we don't have a three components of forces. We don't have three components of forces, we just have two. Okay, and the important thing is to set up the static dynamometer properly in the turret, and once we have established that, we just do the experiment as we normally would. So what are the available technologies to measure the cutting forces? So as said before, we have the piezoelectric dynamometers and we have regular strain gauge dynamometers. And the piezoelectric dynamometers definitely have certain advantages over the strain gauges, including very high sensitivities, and the precision is also very high. But if you see on the negative side, the static measurements are not as good as for strain gauges. This is because we are using a piezoelectric material in piezoelectric dynamometers. Okay, so for the principle of a piezoelectric dynamometer, we must understand how the piezoelectric effect works. Okay, some materials, when a certain mechanical force is applied on them, developed a charge in their body. Okay, and this the amount of charge that is developed is related to the mechanical force that is applied on them. So the ratio between the force that is applied and the charge that is generated is the sensitivity of a piezoelectric material. And it is very important that the relationship between this charge development and the force is very linear. This allows the piezoelectric material to be, this allows the piezoelectric dynamometers to be highly sensitive. In order to showcase the sensitivity of the piezoelectric dynamometers, a small oscille is placed on top of a piezoelectric dynamometer, very similar to 9527B. It is a static dynamometer, and the mass of this oscille ring is 0.33 grams. Okay, so if you see the graph, once the oscille has been placed, you see that the dynamometer is capable of recognizing this mass that has been this mass, or it corresponds to, I think, 0.0032 newtons. Even though the maximum range is 10 kilonewtons, the piezoelectric dynamometers are sensitive enough to capture such small weights. We now look at the different components of a dynamometer setup. So of course we have the static dynamometer with all the sensors, the piezoelectric sensors, and then we have the amplifier, which amplifies the charge that is developed in the piezoelectric material and then converts into readable data. And then we have the DynoWare software. Okay, the digital post-processing is a very important part of cutting force measurements. So a low-pass filter allows us to remove noise from the data that we have captured using the sensor. Okay, so it is very essential to use these digital post-processing to present data that is readable. So a graph that you see here is a typical graph that you obtain soon after you've completed your experiments. But When you apply a low pass filter, you remove all the high frequency noise, which results in a very smooth graph that you see after the application of the low pass filter. Okay, so similar to and very opposite to a low pass filter, a high pass filter removes low frequencies and concentrates on the high frequencies. We basically use a high pass filter in post processing to remove drift that is caused while doing the measurements. Okay. There are multiple reasons for this drifting, and we will just see some of the very common reasons for the cause of drift. Okay, so if a drift is seen in your data, we apply a high pass filter which allows to bring the data in the format that is required. Okay. So, what are the reasons for drift? So, three primary reasons include electric drift because of the amplifier, and something that is, and the most prominent one, something that we see very regularly as we use it in the lab, is an insulation drift caused by contamination to the cable that we use to connect the dynamometer to the amplifier. Okay. Thermal drift is due to high temperatures of machining, which is not usually seen as we do experiments.